Hi guys, hope all of us are doing great. My name is Ernest, and this is Ernest's Sciences and Mathematics TV channel. Today we are going to look at a concept that is basically going to entail the aspect of the Argand diagram. And this basically is a follow-up topic from the concept of complex numbers we had discussed from our first video. Now we had said that basically we have got different types of equations, and one of them was what we referred to as quadratic equations. And this basically, as we said from our first videos, are basically the equations of the form ax squared plus bx plus c, whereby the sum of this specific equation was going to give us the sum of 0. So in this particular case, we said that basically one of the significant applications of equations to model real life situations, and this basically is going to give us the relationship between different variables. So therefore, this nature of quadratic equations are going to assist us find different variables whose basically characteristics are going to be what we refer to as the roots. So in this particular case, there are situations whereby we're going to try and solve the roots of quadratic equations, whereby we are going to see that in some cases we're going to encounter a case whereby the discriminant, as we said, is going to be a negative value. And from that specific case, we said that therefore we're going to obtain roots which are going to be unique in nature, in a sense that they are going to be either imaginary or what we refer to as non-realistic. So therefore, this particular case for imaginary roots, therefore, are going to provide for us an aspect of trying to give them a description. And this, of course, gave birth to the concept of complex numbers. Now, in order for us to try and specify these specific roots from the negative numbers that we're going to obtain, we can be able to put this particular concept of complex representations, whereby we say that we can be able to represent these particular complex numbers using the root of -1, and this, of course, we gave it a notation of given as such. So this one gave an implication that if we have a square over this particular complex aspect, we're going to get it given as -1. Now, in today's discussion, we're going to look at how we can be able to represent this specific set of complex numbers in forms of perhaps a Cartesian coordinate, and this is going to result in the formation of what we refer to as the Argand diagram. So therefore, from our first discussion on the concept of complex numbers, I had mentioned and said that this basically consists of a set of all numbers of the form a plus bi, and as I've already defined the concept of I, so I'm going to presume that that's going to make sense for us. So in this particular case, from this particular representation for a set of all numbers of this particular form, we said that the a and the b in this particular case are going to form what we call a set of real numbers, which you are going to see being represented as such. So therefore, this particular part that is consisting of I is going to form a complex part, which are an imaginary part, which of course I've given as equivalent to the root of a -1 given as such. So therefore, we can be able to conclude and say that the part A is going to form what we refer to as a real part. And then we're going to see that the part bi is going to form the second part of this particular representation, which is going to form what we call an imaginary part. So therefore, the representation of a complex number is going to assume this specific form that consists of the real part and the complex part given as such. So we said that in some of our literature, we are going to encounter this particular form, whereby it is being referred to as the algebraic or the rectangular, or sometimes numbers. Now, therefore, we have forms of a Cartesian coordinate, and in this case I'm going to use a two-dimensional Cartesian coordinate in representing this particular complex number. So therefore, I'm going to have that specific graph, whereby we're going to have this x and y-axis in a two-dimension representation as such. So in representing this particular aspect of the complex numbers, we're going to see that in this specific diagram, we're going to have two variables, whereby we're going to have a as a real part and b I as an imaginary part given as such. So therefore, for us to try and find the relationship that is going to be given by these two particular variables, I'm going to use the y-axis to represent this imaginary part. And in this case, I'm going to denote it using the letter I, and then I'm going to use the x-axis to represent this real part. And I'm going to, of course, denote this one using letter R given as such. So in this particular case, if I'm going to put just an estimation of the representation for those particular parts, so I'm going to just have to divide this specific coordinate in sets of these numbers, so that we can be able to just derive meaning from that. So therefore, I'm going to represent this x-axis in terms of a real part, and this is going to represent an imaginary part for the z or the y-axis represented as such. So therefore, as I've said, then therefore we are going to represent these particular complex numbers by what we refer to as a phasor. Now, in our normal representation of vectors, we said that we're going to use what we refer to as points, and therefore for an arbitrary point, the Cartesian coordinate system for this x and y is going to be represented using a particular point, perhaps 4 points along the x-axis and 2 points along for point B. This is going to be given as such. So therefore, we can be able to give a reference for point B as x and y. So in this particular case, then therefore, it's going to be having a different representation for complex numbers, whereby they are going to be represented by what we refer to as phasors. So this phasor is going to be given an initial z with that specific slash. So therefore, this, in case I use this particular symbol, then therefore it's going to represent a phasor that is representing a complex number. And this phasor is going to be having what we call a magnitude and direction, and in this case, of course, it's going to be just having this normal characteristic of ordinary vectors, as we have said for from this particular illustration of the context under which I'm trying to describe this. So therefore, we can be able to describe a specific complex number. Now, suppose this phasor z is given as 4 plus 3i, then I'm going to use this one as a real part, which is a representation along the x-axis, and this is going to have 4 units. So I'm going to move 4 units along the x-axis, and this imaginary part is going to have 3. So therefore, I'm going to move 3 units along the y-axis. So therefore, this is going to be 4 and 3. Sorry for that. And this is going to be an interjunction and the section between these specific parts. Therefore, from this particular point of the origin, I'm going to have a phasor that is going to be represented using that particular magnitude and direction. So I'm going to have this one representing that particular phasor given as such. So in this case, as we have been doing for normal and ordinary vectors, we can be able to give the angle that is going to be formed between the real part and this phasor. And this I can be able to give it in terms of theta given as such. So that is going to assist us to describe various characteristics, or perhaps trying to analyze this quantity of this phasor using some of the basic laws that we have learned, like the Pythagoras theorem. So in this case, of course, then therefore the description can be able to assist us describe real and imaginary numbers. Now in this particular case, if I give an example of a number 3.8, I can be able to represent this particular number in terms of a complex number, whereby I'm going to assume that basically it has got the real part and the imaginary part given as such. So in this case, the real part is going to be having a magnitude of 3.8, but the imaginary part is going to be having a magnitude of 0. So therefore, I can be able to represent this real number that I've indicated for 3.8 as a complex number by giving it as a phasor set, which is equivalent to 3.8 plus this particular imaginary part given as such. So analogous to that, I can be able to represent a purely imaginary number, for instance, the one that I've given for this case. A complex number that I've given in this particular graph, and this was to I, and this was a representation. So that set represented the complex number. So suppose I have a purely imaginary number like 3i. So this is going to, which is going to be under 3 units, and therefore I can be able to give this one as well as an imaginary number that is going to be only imaginary and considered as a complex number having a 0 real part. So this one can be given as a 0 plus 3i given as such. So suppose I'm going to try and give a graphical representation for these two specific scenarios, perhaps for this one and this one. Can be able to have two sets of graphs for this one given as such. So, and then I'm going to give the second one given as such, whereby I'm going to have a real and imaginary set of numbers along those x and y direction respectively. So for the first one, I'm going to have the phasor set represented by a real number, that is 3.8 given as such. So therefore, if this is a real number, then therefore I'm going to represent this one using the x axis given as such. So therefore this is going to be a continuation of numbers along that one, and for the imaginary number I'm going to have 2, 3. So therefore this basically is going to be a representation along the real part, whereby we're going to have this one represented as 3 units along this, and that is going to have that phasor given as such. So suppose we have an imaginary number that is only represented by 3 I given as such. So therefore we are going to have it as given as 1, 2, 3, 4, and this is going to be 1, 2, 3, perhaps 4, and then we're going to represent this one along the imaginary part for the 3 units given as such. So it's going to be of course indicated using that particular notation, and of course these are just solid lines. I'm just trying to repeat them for emphasis so that we can be able to be seeing them, or rather they can be feasible for us. So basically the concept of representing these numbers in form of a Cartesian coordinate is going to give the concept of a Argand diagram, and this basically the diagram that I've given using this representation is referred to as the Argand diagram. And we're going to see different ways in which we're going to perhaps represent different phasors using this particular diagram that I've shown above. So catch us in our next videos. We're going to look at different ways in which we can be able to describe perhaps other aspects or characteristics of complex numbers, and these are going to assist us, of course, solve part of the equations which are going to entail basically the aspect of complex numbers. So therefore, hope that this is going to assist us in trying to form, of course, other areas that are going to deal with the concept of a Argand diagram. And I'd like to request our members to kindly check our description boxes for various links of other similar videos. So that is it for now, guys. Bye, God bless you.